as always, you have a unique opportunity, not unique, but maybe perfect opportunity to ask your questions. So if you have any questions, any doubts, anything you'd like to share with me, then just say it. I have an opportunity, because you can read Shriv, you can read Zastavnyak, you can read Bald, you can read Shriv. There are a lot of good books on stochastic calculus, much better than my handwritten notes. So my only advantage over these books, over these great books, is that I can answer a question. Basically, that's unique advantage. So be brave, don't be shy. Okay, if you have no question, then let's solve some exercises. I would prefer, honestly speaking, I would prefer your questions, but anyway, we are ready. Okay, let's solve some exercises. Consider xt, that is t times wt plus integral from 0 to t uwu squared dwu squared. W always denotes Wiener process. And my question is, first, find dxt and check whether xt is a martingale. Second point, find expected value of xt and variance of xt. So let's start. I give you 3 minutes to solve the first one, and then we will discuss. It's better to foster your work. Just 3 minutes to solve the first one. You will need basically to understand what is a shorthand notation and to apply simplest Ito's lemma. We have stated 3 Ito's lemma. Simplest one, a little bit more general, and the most general. So for this, just you can write your answer in the chat, or you can just say it loudly. Say it loud. Okay. How is going? Anyone is trying to solve? Have you got stuck? Have you got the full answers? What's going on?
We are trying to solve.
Okay, that's great. The first one, point A.
So I suppose dxt is just tw squared t.
Sorry, t
W times w t squared.
T squared?
No. W squared, I mean.
Like this?
dt.
Sorry, I don't understand. T times what?
W squared t dt.
Like this?
I suppose, yes.
You are partly not quite so. So
I suppose.
Yeah.
Answer.
Okay.
Just VT, WT plus t multiplied with the wt plus something.
Like this.
Yes.
Not quite so. Okay. Let's. Okay, so
May I
first,
suppose an answer?
okay, yeah.
In brackets, WT plus TWT
WT times
plus, no, plus T multiplied by WT.
Multiply.
No,
Like
T
this?
multiplied by WT.
Uh-huh.
Then brackets, DT plus brackets, T plus TWT squared, DWT. That, yeah. TWT.
GWT. That's much better, but that's the closest answer to the truth, but with one small mistake. Okay, let's solve it, I think, completely. But okay, so but it's rather close to the correct answer. Okay, so I see two parts in my question. So first, let's deal with the second part because it's easy. When we see some integral of hedgehog u du plus integral from elephant u dwu, we just transform it into, this is full form. And in short form, it will be hedgehog t dt plus elephant t dwt. This is shorthand notation. Once again, shorthand notation has no meaning by itself. So it's meaningless to write something like dx is written to wt plus something, because this object is non-existent, and this is a honest random process. So that can be like this. Shorthand notation is meaningless by itself. Okay. So I see that is integral. So in shorthand form, it will be part that correspond to TWT, and the part that correspond to this integral will be just exactly T times WT squared dWT. So that's by definition of a short form. If you have an integral in a full form, in a short form, it just you drop the integral sign and you replace the index. Basically, one part is done. Okay, what about this one? Here we will use Ito's lemma. Ito's lemma says that when you have a function of t and wt, in our case, that's just the product of t and wt, then Ito's lemma says that dyt, you need to take f prime with respect to t times dt plus f prime with respect to w times dwt plus correction term 1/2 f prime prime ww dwt squared. In our case, I will have dyt, that is wt times dt plus t times dwt plus 0, because second derivative with respect to w is 0. The wt enters linearly in our expression. So here I have wt dt plus t times dwt. So that's the correct answer. The closest one was the third. The first one was, there was this part correct, but everything else was not correct. But this part in the first answer was okay, and in the second answer that was a mix, that dx was equal to wt, but that's not okay when something imaginary, something shorthand is equal to real process. That cannot be so. Okay, any questions with point A?
Yep. May I ask a question? Why don't we why we consider that y f of twt is twt, not twt plus the integral? It's also a function, no?
Yeah, but it's a very difficult function because it involves, yes, you may, but in this case, it's very hard to apply Ito's lemma, because Ito's lemma says when you have a function, ordinary continuous function, and the integral, it involves, so basically, this is just the statement of Ito's lemma, yeah? You have a function of t and wt. And for this integral, you cannot directly use Ito's lemma for that part, yeah? Because xt depends on wt minus 1, on wt minus 0.5, because this integral is influenced not only by wt, but also by wt over 2. So imagine here only wt influences that part, but here wt minus 0.5, wt minus 0.7, w, I don't know, t over 2, all these terms, they enter this integral, yeah? This integral depends on many values of w. It's the integral, so it depends on the whole trajectory of wt. So this part depends only one value of wt, and the integral depends on the whole trajectory of from w0 up to wt. And Ito's lemma is designed to work only with a very simple case when you have a function of final value alone. Okay.
Okay, but couldn't we integrate the function uw squared, find the value of integral actually?
No, you have no usual rules that can be applied. Ito's lemma can be applied. You have so rules of integration are different.
So when we have the integral with dw the usual rules of integration can be applied, right?
Yeah, because
okay. Yeah,
that was our first example. Do you recall our first example? Integral from 0 to t wu dwu. If you just apply usual rules, it would be something w u squared over 2 from 0 to t. It would be wt squared minus w0 squared divided by 2. It would be wt squared over 2 if you apply usual rules.
yeah,
But
yeah.
we have proven by taking a honest L2 limit, we have proven that it will be equal to wt squared minus t over 2. That's a very strange correction term, which says that usual rules do not apply when you do stochastic integration. No, I would them. So usual rules, we cannot use them.
Okay, thank you.
So then how to do stochastic integral? We have working rules. One working rule is Ito's lemma, but Ito's lemma says, oh, I can say you how to calculate some relations between integrals, but when yt depends on t and wt, okay? So yeah, you have some just, why just not integrate like w cube over 3? No, that's not possible.
Yeah, okay, thank you very much.
Okay, maybe just to not turn the page, because we have found expression for dxt that is fast xt. Is it a martingale?
No,
No. Why?
because it has the term something dt,
Yeah,
which
because it has term something dt. Yeah, because of that term.
it may be so do I get it right that the term dt refers to the trend part?
Ooh, I think you have no strict definition what is a trend. So when you will define it, maybe it will be. But why you have no such definition, I would avoid such terms.
Okay, okay.
Yeah, because of the term, yeah, you are right that xt is not a martingale. I would not call it trend. Why I would not call it trend? It adds a little bit of predictability, but it's not a trend. So imagine, so why it's a problem? So imagine a process zt that is just integral from 0 to t wu dt. At first glance, it seems, oh, I have something with expected value 0 inside it. Why it's not a martingale? But look carefully. Imagine that you know, so imagine why it's not a martingale. So I will explain. Intuition is not a martingale. It's not a martingale. It's not like a trend. Because
No, I mean, there is something in the equation, in the final equation, which is dependent on time, not on the winner process, but on time.
I would be careful. Just imagine what happens. So imagine that at time 1, this is t, this is wt, and imagine that wt, you are here. So this is a plot of wt. And if small, so you have current value of z1. So z1 is, you have current value of z1. If you consider small change of time, 1 plus small delta t, yeah, Brownian motion will change a little bit. Yeah, it may go up, down, but not too much, because variance of future increment is just delta t. And obviously, this wt with high probability, in my case on the picture, will remain positive, because I consider a small interval of time. And if now the value of w is positive, then for a small change of delta t, the future value w1 plus delta t will be positive with high probability. And so this integral will include a term like w times delta t, and it will be positive. So in this case, I predict that zt will go up, okay? If the future change of zt is positive with high probability and negative with low probability, I expect in this particular case that zt will go up. But on the reflected path, I would expect that zt will go down. So I have some information in zt that helps to predict future value, future changes of zt. Future changes are not, for a martingale, future changes should have expected value 0, okay?
Yes. Yeah.
Excuse me, can you please once again explain the logic of what you did?
The logic for martingale.
No. Previous on the previous list about dxt. I mean, the final. What is the final value of dxt?
Here.
And so dxt includes dxt.
No, dxt equals 2. Sorry.
Ah,
Yeah,
okay.
you're right. It's equality sign. Yeah. It was just a misprint. Yeah, I agree.
Thank you.
The xt has two terms, one provoked by TWT, the second one provoked by the integral. Okay, let's move on. Let's calculate expected value of xt. What is the expected value of xt? It's easy. I think 2 minutes are enough. Just I give you time to calculate expected value of xt. Okay, what is the answer? That's easy. That's really easy. Okay, just plug in the value of xt. Maybe there are answers.
Wait
in
a
the
second.
chat. I just plug in what is known, and it's very, very very fast.
Isn't it x0 plus t?
No. So I just plug in the value of xt, and basically, bingo! It is expected value of TWT plus expected value of an of a stochastic integral. We have property that expected value of stochastic integral is
0.
Zero. It's any hedgehog will do, provided some convergence, but we will not check it. And here t may be taken out of the expected value because it's non-random, it's time. There are nothing random in time. Yeah, you are right. It's 0. Yeah. Okay.
So it may be anything like inside the hedgehog, like any ugly function will give us 0. We expected value 0.
Not too ugly. There are some mathematical exceptions, but we will not check these. So there are some exceptions when assumption. So we have an assumption, hidden assumption that integral from 0 to t expected value of hedgehog squared du is finite. Finite. Okay. So, but we will not check it. So we will believe that there are no exceptions, but there are some exceptions to this rule.
So in general, it's not always, but for us, it will be always true.
Yeah, because this condition may be violated.
But we will not check that, neither on exam.
Yeah.
Okay, thank you.
Could you please briefly one more time explain why the expected of the integral is 0? Because we move the expectation operator inside, right? And we get the expectation of...
No, we don't move it inside. Just we have discussed it previous lecture. Because basically, what we do here, we invest in a Brownian motion company. So imagine so it's not basically a honest proof, but it's a good intuition. So you buy shares of Winner Process company. The price of its shares is just a Winner Process. So when you are using some trading strategy, future increments of price, future increments of Winner Process are independent and positive and negative with equal probability. So when you have 5 shares of Brownian Motion Corporation, they can go up, they can go down with equal probability. And so expected value of your profit is 0. Okay. The intuition behind, but
Yeah.
if you like to go to, let's say, sums, so it will be some function. So it will be the limit of a big sum, and in this sum, every term will be something like hedgehog times u multiplied by wu plus small delta minus wu. So you multiply hedgehog by a small increment. And this is independent of hedgehog because hedgehog is adapted to some filtration. They are independent. And as they are independent, the expected value of a term in a big sum, because integral is just a sum, the expected value will be expected value of hedgehog that may be positive or may be negative, but expected value of increment is 0. So basically, that's the idea of the proof. If you like a honest proof, I think it's presented in Zastavnyak, in Baldi and Shreve and Steele for sure. In Zastavnyak, I think yes. Okay.
Yeah, okay, thank you.
And Brownian motion and Winner Process is actually the same, and you can use it interchangeably, or okay.
Some authors do make a subtle difference, like Winner Process is a mathematical model and Brownian motion is the actual physical process. We observe movement of air particles and so on. So in some sources there is a distinction. Brownian motion is a physical process, real one, and Winner Process is a mathematical model for it. But for me, I will not make such a distinction.
Thank you.
Okay, so it's 0. With variance, it's a little bit harder. Let's move on to the next page. Variance. So this one is a little bit tricky. Variance of, I just plug in my expression, TWT plus integral from 0 to T U WU squared DW U. And it's variance of TWT.
Sorry, isn't it t cubed?
Of the first term, yes. Of the first term, it's t cube. But it's not the final answer because you have more terms. Yeah, of the first term, yes, you're right. But you need also 2 covariances. And with covariances, it's a little bit, but the covariance is not 0 here. It's okay, we will solve it. But I think the main problem, the main difficult step is covariance. Because yes, with this, I agree, it's the value of the first variance is
T cubed.
T cube. Do we need some explanation or it's clear?
It's clear.
Yes, yes, we need.
We need, so because T is non-random, T is just time, you can take it out of the variance, and the variance of TWT is just T squared variance WT is T squared times T. Okay?
Yeah, thanks.
Okay, let's move on to the second term. So let's stop and let's do each term separately. Variance of an integral from 0 to t u w u squared d w u. Which property can we use? Who can find in the list of properties of stochastic integrals the property that can be used?
Yeah, this should be the integral from 0 to t, the expected value of the hedgehog squared.
Yeah, this property is called Ito's isometry. Ito's isometry. And yeah, we just transform stochastic integral into Riemann integral. And we interchange squaring the integral and squaring the integrand. So it will be u w u squared. Yeah, you are completely right. So it will be integral from 0 to t, expected value of u squared w to the
And,
power 4.
Now we can use, right, the regular rules of integration because we have du.
Yeah. When you have du, when you have Riemann old friend, your old friend Riemann integral, yeah, as always with old friends, they're good. Yeah. Yeah, you can recall all the past glory, all cosine of x minus sine of x and so on. Yeah. All the rules do apply in this case. U squared is non-random, so I take it out of the expected value.
It should be wu to the power 4, right?
Yeah. And we have calculated last time, I think, expected value of w to the power 4. What was the value?
3t squared.
Yeah, exactly. We have calculated it to avoid the already calculated du. And last time, I think. And it's integral from 0 to t, 3u to the power 4 du. And it's our old friend. You can recall, let's say, high school. Yeah. 3t to the power 545. Okay.
Yeah.
Now for the most difficult part, we need to calculate covariance of t times wt with an integral from 0 to t u times wu squared dwu. First, once again, this t is non-random. It's a moment of time. It has nothing random. So I can just move it outside covariance. Wt and some integral, some hedgehog u dw. Okay, we have covariance in Ito's isometry. Yeah, we have covariance for Ito's isometry, but in our lecture we have stated covariance of two integrals. So if you look at the properties of stochastic integral, we have stated how to calculate covariance of two integrals, integral from a dw and integral from b dw. In this case, the second term is stochastic integral, but the first one is not, but we can easily represent it as a stochastic integral. So we will represent wt as a stochastic integral from 0 to t dwu. What should I write here to represent Wiener process as a stochastic integral? What should I write inside? Yeah, Elisa is completely right. We can just write 1 there.
Is it like by applying regular rules, or
No, we have no regular rules for stochastic integration. Once again, we have no regular rules for calculating stochastic integrals. We have two ideas that can be used. We have Ito's lemma, or maybe 3. Ito's lemma. We have a full short-term correspondence, and we can integrate piecewise constant processes using the idea that stochastic integral is a profit. And integral is just profit. This intuition can be served as a definition for piecewise constant processes. So in this case, if I have 1 share of Brownian Motion Corporation, and I just hold 1 share of Brownian Motion Corporation, in this case, at the beginning, my wealth is 0. At the end, I have 1 share with price WT, and my welfare is WT. Okay. So basically, I apply this idea. The problem is that you cannot apply standard rules for calculating Ito's integral. So maybe you are right for such a simple case. Yeah, for such a simple case, it works. Yeah, but even for this case, it's not WT squared minus W0 over 2. The correct answer is WT squared minus T over 2. Yeah, so you cannot apply Riemann integration rules to calculate stochastic integral. Okay, so we may apply 3 ideas: Ito's lemma, full and short-term correspondence, and in the case of piecewise constant process, just calculate as a profit. Okay.
okay,
Yes.
thank you.
Boris, am I right that if we have a constant inside the integral, it means that at some period of time we just buy or sell an amount of shares, and then we're till the end of time we're doing this.
Yeah, we buy it, we hold it, we sell it. Yeah. Or you may even think that your grandma, your grandma has left you 1 share, and you just observe the change of your welfare. You don't sell it, you don't buy it. If it's constant, you can just check your welfare. Yeah. Oh, in the beginning, my welfare was W0. At the end, my welfare was WT. So the change in my welfare is WT minus W0. Okay.
Which
you
is
can
0 and which is WT.
Yeah, WT minus 0. Yeah, it will be WT. Yeah.
Yeah. Okay. Thank you.
Okay, so the covariance in question will be T covariance between integral from 0 to T1 dWu, and this may be calculated. We can apply Ito's lemma. Oh, sorry, not Ito's lemma, Ito's isometry, and it says it integral from 0 to T, expected value of the product 1 times UWU squared. And the main point is that we have obtained all the friend where we can use standard rules. Now we can use standard rules of integration. It will be 1 times U du. And it will be T squared over 3, yeah?
Yes.
And final answer, if I collect all the terms. The variance of xt is t to the power 3 plus 3t to the power 5 over 5 plus 2 times t to the power 4 over 3. Okay.
I'm sorry, Professor, but
Yes.
haven't we forgotten the t in front of the covariance?
Ah, yeah.
Then it's t to the power of 4.
Yeah. Yeah, you're right. Okay, we go on.
Boris Borisovich, may I have
Mhm.
a question, please?
Mhm.
What should we do if we have under the integral not dwu, but du in the covariance?
In general, it's hard to say. So the main, it's hard to say. There are no simple formula for that. Sometimes you can go from stochastic integral using Ito's lemma. You can go to Riemann integral. So maybe using Ito's lemma in your imaginary case, you can go from Riemann integral to stochastic integral. Maybe. So in general, there are no simple formula. In some particular cases, you can go from Riemann integral to stochastic one because Ito's lemma gives us a link between the two sometimes, if we are lucky. And basically, that's first strategy that I see. The second
Okay,
strategy you can
I
simulate,
get it. Thank you very
but
much
no
for the
simple
answer.
answer for your question. Okay, let's consider the next. So we have solved the exercise and then finished. Let's consider Girsanov theorem. The idea of Girsanov theorem is simple. The Girsanov theorem is more or less complex, but the idea is very simple. Imagine a random variable x is just a random variable. Values are 0, 1, and 2, and the probabilities that x is are 0, let's say 0, 4, 0, 1, 0, 5. In this case, expected value of x is just 1.4, okay? And my question is the following. My question, can you change probabilities in such a way that expected value of x is 1 and the new, not, so this is old expected value, yeah? So I will write, can you change probabilities in such a way then new expected value of x will be 1 and variance of x, new variance of x will be, let's say, just a moment, 4 times, let's say 0.5. Yeah. Can you change probabilities in such a way that expected value of x is 1 and variance is 0.5?
Probably yes, why not?
Uh,
Or we should prove this.
Probably yes. Yes, why not? Probably no, why yes?
Okay, okay.
Okay, so what we should have? We should have, it follows that expected value of x should be 1, and the new expected value of x squared should be 1.5. Yeah.
Yes.
So you should have two equations. So if these new probabilities p star of x equal to alpha, beta, and 1 minus alpha minus beta, and we should have, maybe it's better to have, maybe it's better to introduce alpha there.
Maybe we
beta there.
cannot change. Because in this case, the probability of x equals 2 should be negative.
Why?
Well, I got it from the equations.
Let's check. I think you are. Maybe. But let's try. Let's check. So this will give me 1 times alpha plus 2 times beta should be 1. Yeah. This says me that 1 times alpha plus 4 times beta should be 1.5. Yeah. Okay.
Yes.
Maybe you're right. I don't know. So let's subtract. We have 2 betas is 0.5. Beta is 0.25.
It's okay, actually.
And I think alpha is 0.5.
Yes.
And I think everything is fine. Okay. I think everything is fine. Now, this was the idea of Gersanov theorem. So sometimes you can change probabilities to obtain desired expected value and desired variance. Okay. And now let's go to the Gersanov theorem. So sometimes you cannot, yeah, because if I would request an expected value of x squared equal to, let's say, 10, it would be impossible because 1 alpha plus 4 beta is obviously less than 5, yeah, because alpha and beta are probabilities, and when you add alpha plus 4 beta, you cannot have 5 or 6. So sometimes you can, sometimes you cannot. So the theorem is not obvious. So Gersanov theorem says that if WT is a winner process with respect to filtration FT under probability P, and WT star is WT plus alpha times T, then there is a probability P star such that WT star is a winner process with respect to filtration FT under probability P star. So let's so we will not prove it. We will just get a little bit familiar with this theorem. So let's solve. So we have modified winner process, and we have modified probability in such a way that WT is a winner process with respect to P, and WT star is a winner process with respect to P star. Okay, let's solve an exercise to get used to Gersanov theorem. Imagine that WT is a winner process with respect to FT under P, and WT star equals to WT plus 2T. So by Gersanov theorem, there is a P star such that WT star is a winner process under P star. And so my exercise is calculate probabilities that W1 is greater than 0, probability that W1 star is greater than 0, probability star that W1 star is greater than 0, probability star that W is greater than 1. B, expected value of W1, expected value of W1 star, expected value star of W1 star, and expected value star of W1. And C, calculate, let's say, variance of W1, variance star of W1, I don't know, variance of W1 star, and variance star of W1 star. I think that's enough to feel the difference. Okay, let's go on. So first question is very easy. As W1 is winner process with respect to some filtration under probability P, then W1 under probability measure P has normal distribution with mean 0 and variance 1. And probability that W1 is greater than 0 is
0.5.
exactly, because it's symmetric like this. Okay, what is the probability that W1 star is greater than 0? But W1 star is just W1 plus 2 times 1. Its probability that W1 is greater than -2. And we can remember that for standard normal random variable, and in our case, it's a standard normal random variable, with probability 95%, it will fall between -2 and 2. And
0.975.
yeah, it's 0. So I should remove the left tail, 2.5%. And you're right that the answer is almost 1. If I calculate probability stars that W1 star is greater than 0, then it's easy because we have a match.
Should be 0.5.
Yeah, because W star, so when everything is start, it's easy. When everything is not start, it's easy because W star is winner process with respect to some filtration under P star, and that's 1/2. What is the start probability that W1 is greater than 0? It's difficult to change probability, but it's easy to replace W1 by W1 star with corresponding shift. So it will be P star of W1 star minus 2. It's P star that W1 star is greater than 2.
0.025.
Yeah, I agree. Any questions here?
So could you please one more time briefly explain the fact that P W1 without star, the probability is the same as P star W star? Is that
Yeah,
if we
because-
change the winner process, then we can find the probability and the probabilities remain the same? Is that right?
So you change probability measure, but new process on the old process WT was a winner process under old probability, and new process WT star is the winner process under new probability P star.
Я подумал о том, что ты мне говорил про очки. Я думаю, это хорошая идея.
Very well. Let's. Okay, can we continue?
Boris Borisovich, but it is not clear for me, how do you understand that P star of new winner process more than 0 is 1/2?
Because it's a winner process. What is the definition of winner process? That W1 star under P star has normal distribution with mean 0 and variance 1.
Oh, okay. So we just obtain new winner process with the same properties as the old winner process had. Just normal
Yes,
distribution,
five
variance.
5 properties of winner process. For any winner process, these 5 properties do hold.
Clear. Thank you very much.
Okay, let's calculate expected value. So 2 minutes for you to calculate these expected values.
У вас связь пропала?
No, everything is fine.
А,
Just you have 2 minutes and I don't see any answers yet.
No, the first one is 0.
And the second, the third, the fourth.
Third,
Yeah.
also 0.
Yeah, these are when you have no star, that's easy. It's 0. When you have star, that's 0. And the last 2 are correctly written by Elisa. So it will be 2, and that one will be -2. Do we need some explanations?
Yes, please.
Okay. So expected value of W1 star. Once again, it's easy to change inside expected value than expected value itself. So I just write W1 plus 2 times 1, the definition of W star. And it's 0 plus 2.
Why is it times 1 and not times t?
Sorry?
Why is it times 1 and not times t?
Because it's W1.
Oh, okay, clear.
That's okay? Do we need more comments?
No, clear.
Clear.
Okay, and the last with variance, 2 minutes for you.
Can I give an answer?
Yeah.
It's only once for every term.
Yeah, it's 1, 1, 1, 1, 1, 1, 1. Yeah, I agree that it will be 1, 1, 1, and 1. Yeah, I completely agree with you. So I will just solve one of them, let's say that one. What is the variance of W1 star? It's the variance of W1 plus 2 times 1, but the constant does not influence variance. So it's variance of W1 and it's 1. Okay. And now let's solve the last small exercise. So we get used to Gersanov theorem. Next time we will use Gersanov theorem to price European type contracts in the framework of Black-Scholes model. So it will be next time. Maybe you have maybe you looked through past exams and you have solved some. You have seen some exercises like find the price of a European type asset, even that. Okay, so the last exercise for today. In the framework of Black-Scholes model, DST is assumed to be mu ST dt plus sigma ST dWt. Mu and sigma are constants, and Wt is always within the process. And my question is, consider Yt, that is logarithm of St. And my question first, apply Its lemma to find dyt. And my second question is just write St as a function of t and Wt. So my first question is find Yt, and my second question, write St as a function of t and Wt. Okay, the goal is clear?
Yes.
Okay, let's apply Its lemma. So I take first derivative with respect to s. So first derivative is 1 over st times dst plus 1 over 2 times second derivative. What is second derivative of logarithm?
Minus 1 over st squared.
Exactly. Times dst squared. Then I will just plug in this ds here, and I will plug in ds there, and I will use symbolic nonsense simplification rules like dt times dt is 0, dt times dwt is 0, dwt times dwt is dt. So this is nonsense, but these mnemonic rules help us to obtain a correct full form. So this is garbage by itself. dwt does not exist. So we cannot have something that is multiplied by, so these are not numbers. So this is just mnemonic rule. But it helps us to recover correct, so the correct expression will be full final form. Okay, let's just plug in. Okay, dyt is just 1 over, I just plug in and I obtain mu dt plus sigma dwt. So that's the first term, minus 1 over 2 times st squared times mu st dt plus sigma st dwt squared. Yeah, I just plug in everything I need. When I will calculate the squared value, this one will be squared, but dt squared is 0. This one will be squared, but dwt is sigma squared st squared dt, and plus 2 times 0. Yeah. If you recall, a plus b squared is a squared plus b squared plus 2 times a b. Yeah.
Yeah.
Okay. Finally, I have dyt is mu dt plus sigma dwt minus 1/2 sigma squared dt, or dyt equals to mu minus sigma squared over 2 times dt plus sigma dwt. This is nonsense. It has no meaning by itself, but we can recover the full form. Yt is y0 plus stochastic integral plus ordinary old Riemann integral mu minus sigma squared du plus integral from 0 to t sigma dwu. So that's a correspondence between full form and short form. I recall that yt was logarithm of st. So logarithm of st is a logarithm of s0, and these two integrals, I can take them. It will be mu minus sigma squared over 2 times t plus sigma wt. And finally, I obtain st is just s0 times exponent of mu minus sigma squared over 2 times t plus sigma dwt. And I think we have done the whole exercise. We have st is the explicit function of t and wt.
Boris Borisovich, may I have a question, please?
Yes, if you have some question, let me just number all the steps to make it a little bit easier to.
The fifth one.
Yeah.
Where did our integral disappear?
Which one, Riemann or stochastic?
Both.
Just take this. I believe in you. Be brave. My heart is with you.
So you calculated them and then
Yeah.
substituted to the yt.
Because it's a constant. Yeah, it's a constant. So these are constant. So if you integrate something like 7.
Yep.
So you will get 7t. And for that one, we have a interpretation. If we have both sigma Brownian Motion Corporation shares, and our initial welfare is sigma times 0, sigma times the price, our final wealth is sigma times final price WT. So our gain is sigma times WT minus sigma times 0. So in this case, when the integrand, the integrated function is piecewise constant, then we can apply intuition that stochastic integral is just a change of welfare, a profit. And basically, here it is. Okay.
Thank you very much for the intuition and explanation. I have understood everything.
Okay. Yeah.
So as I understand, recalling the Black-Scholes models, what we have here is the price of the share, right, at period t. This is the sixth equation.
Yeah.
But could you please explain what is the meaning of what we are given from the very beginning? That dst or mu st, just the short form of the integrals.
Yeah, it's a short form of integrals. So if you like intuition behind it, so the intuition behind this, imagine a small time difference, small time lag. Delta t is small. So without this term, the price of share will be completely predictable. It just will exponentially grow with some rate mu. So mu is the rate of, let's say, deterministic growth. If sigma would be 0, then if you look at the final expression, if sigma is 0, then basically
It's just
ft
exponentially.
is just the exponent of mu t. Okay, so this is the first part. So it's a rate of change. So it's like rate of price growth. Yeah, okay. So mu is a growth rate. And this term, it brings randomness in the price of a share. So basically, if I consider small delta of time, delta of price is governed by deterministic positive term plus non-deterministic random term that can be positive or negative. So basically, this says that the change of price of a share is proportional to the price. Okay, so when the price is big, big price is multiplied by change of Brownian motion, and change of Brownian motion may be positive, may be negative with equal probability. So it may go up, may go down. Okay.
Yes, yeah, thank you. So, but it means that in this case, DST will actually has a meaning, right? It's like the change of the price of a share.
But this comes mainly from the meaning. But this comes mainly meaning. Okay, intuitive meaning, but no honest. Okay, I maybe agree with you that it may hide some intuition, but not a honest. So okay, maybe I would agree with you that DST has some intuition behind it, but it's not a well-defined mathematical object. Okay.
Yeah, now I got it. Yeah, yeah. Thank you, thank you.
Okay, you cannot take expected value of DST. That's a nonsense. Yep. But yes, intuition, imagine a small delta of time and so on. Okay.
Thank you.
Okay, so we have solved all the problems. Next time we will speak about pricing European contracts in the framework of Black-Scholes model. We will use Gersanov theorem for that. We already are a little bit familiar with Gersanov theorem and with Black-Scholes model. So basically, that's all. Have a nice day. Be happy, stay safe, and so on. Bye-bye.
Excuse me.
Bye.
Can I have
Yeah.
a question?
Yes, you can.
We've
That's my
got
only advantage.
we've got a missed seminar, the first one. So could we please get it somewhere?
Sorry, I don't understand.
We missed the first seminar, as I remember. Yes?
Yes, we will compensate it. Don't worry.
Okay, thank you. I think it will be of value for us.
Okay.
Okay, thank you.
Borisovich, can I also ask a question?
Yes.
If we go back just to the beginning when you made a graph with why that T is not a martingale, could you please once again explain why did we? Yes, here this is.
So for a martingale, the future change, let's say 1 plus delta minus m1, given all the information, should be 0. Okay. For a martingale, the expected value of future change given current information is 0. Okay, or restated. So you may just write expected value of m1 plus delta given f1 is m1. Yeah, so that's the same thing. Expected change, expected future change should be 0 given current information for a martingale. Okay.
Yeah.
And consider a small delta of time, small delta. What is the expected change of this integral? The expected change of this integral is current value of W multiplied by small delta. But if current value, current WU is positive, then you expect a positive change. So roughly speaking, you can say that this is roughly, if delta is small, then it's roughly delta W1 times delta, okay? Because this integral just sums delta t times current value of WU. So given F1, it will be W1 times small delta. And if you know that W1 is positive, then you expect positive gain of ZT, okay?
Yeah, yeah.
And for a martingale, the gain, the expected future gain, independently of current value, should be 0.
Got it. Thank you. And here, like we have WU times delta t is greater than 0. I thought, like, isn't delta t just scaling, but we still do not have like knowledge about where it will go. WU can go positive.
When you check martingale condition, you imagine that you know everything up to time s. So I know everything up to time 1. So
yeah.
I know W1. And for me, I'm sure that I see positive W1. And given positive W1, I predict positive change in process Z. So process Z is not a martingale because given my current information, I'm making non-zero prediction of future change of Z. And for any martingale, for any current state, the prediction of so what's a martingale condition? So M, let's say S plus delta given Fs is Ms, or stated differently, expected value of Ms plus delta minus Ms given any current information is 0. So this is a definition of a martingale. In the definition of a martingale, it's stated that given any current information, any current state, your best guess of future is that process will on average not change. It may go up, it may go down, but independently of information I have, my best guess should be 0. And I have drawn a picture that my information is sufficient to predict positive changes in Z.
Yeah.
So that is not a martingale.
Understood. Thank you very much.
Okay, so bye-bye. See you next time.
Boris Borisovich, may I have a very small question about the integral? Do we have here du, not dt? It's just a question for understanding.
Yeah, du, yeah, you are completely right.
Okay.
Yeah, because otherwise it's
yes.
The upper limit and the integration should not coincide. Yeah, you are completely right. Thank you.
I got it. Thank you very much for the lecture.
Okay, bye-bye.